chemical kinetics and stability. In the rational design and evaluation of dosage forms for drugs, the stability of the active components must be a major criterion in determining their suitability. Stability is defined as the study of the extent to which the properties of a drug substance or drug product remain within specified limits at certain conditions such as temperature, humidity, light, etc. The chemical kinetics is defined as how drug changes with time, which is the study of rate of change. Many drugs are not chemically stable, and the principles of chemical kinetics are used to predict the time span for which a drug, pure or a formulation, will maintain its therapeutic effectiveness or efficacy at a specified temperature. Several forms of instability can lead to the rejection of a drug product. First, there may be chemical degradation of the active drug, leading to a substantial lowering of the quantity of the therapeutic agent in the dosage forms. Many drugs, such as digoxin and theophylline, have narrow therapeutic indices, and they need to be carefully titrated in individual patients so that serum levels are neither so high that they are potentially toxic nor so low that they are ineffective. For these drugs, it is of paramount importance that the dosage form reproducibly deliver the same amount of drug. Second, although chemical degradation of the active drug may not be extensive, a toxic product may be formed in the decomposition process. Previous investigators described several examples in which the products of degradation are significantly more toxic than the original therapeutic agent. Thus, the conversion of tetracycline to epianhydrotetracycline, arsphenamine to oxofenarcine, and para-aminosalicylic acid to meta-aminophenol in dosage forms give rise to potentially toxic agents that, when ingested, can cause undesirable effects. Also, previous investigators reported that the anti-malarial chloroquine can produce toxic reactions that are attributable to the photochemical degradation of the substance. Phototoxicity has also been reported to occur following administration of chlordiazepoxide and nitrazepam. Another example of an adverse reaction caused by a degradation product was provided by also previous investigators, who showed that infusion of degraded penicillin G led to sensitization of lymphocytes and formation of anti-penicilloid antibodies. Third, instability of a drug product can lead to a decrease in its bioavailability rather than to loss of drug or to formation of toxic degradation products. This reduction in bioavailability can result in a substantial lowering in the therapeutic efficacy of the dosage form. This phenomenon can be caused by physical or chemical changes in the excipients in the dosage form, independent of whatever changes of the active drug may have undergone. Fourth, there may be substantial changes in the physical appearance of the dosage form. Examples of the physical changes include mottling of tablets, creaming of emulsions, and caking of suspensions. Although the therapeutic efficacy of the dosage form may be unaffected by these changes, the patient will most likely lose confidence in drug product, which then has to be rejected. A drug product therefore must satisfy stability criteria chemically, toxicologically, therapeutically, and physically. There are several factors that might affect the chemical degradation of a pharmaceutical compound. These include the concentration of reactants, concentration of products, concentration of other chemical species, temperature, light, pH, humidity, the solvent that is being used, and pressure. Order of reaction. Concentration of reactants is one of the factors that might influence reaction rate. Reaction rate is given by the expression dC by dt, where dC is the increase or decrease of concentration over an infinitesimal time interval dt. According to the law of max action, the rate of a chemical reaction is proportional to the product of the molar concentration of the reactants, each raised to a power usually equal to the number of molecules of the reactants undergoing reaction. The order of the reaction provides a measure of the influence of concentration of reactants on the reaction rate. It is the number of molecules of the reactants whose concentration influences the reaction rate. In the reaction of acetic acid with ethanol, the reaction is first order with respect to acetic acid and first order with respect to ethanol, and the overall reaction is second order. Suppose that ethanol is in great excess as a solvent, the concentration of the ethanol will remain essentially unchanged. As we mentioned, the driving force of a chemical reaction is proportional to the molar concentration of the reacting substances, each raised to a power of the number of molecules of the substances participating in the reaction. If reaction occurs between two reactants A and B to give a product, then the rate of the reaction is proportional to the concentration of the reactant A to the power m and multiplied by the concentration of the reactant B to the power n, where K is a reaction rate constant, and the order of the reaction is the sum of the exponents m plus n, and the order with respect to A, reactant A equals m, the order of the reaction with respect to B is n, and the overall order of the reaction is the summation, which is m plus n. A reaction whose overall order is measured can be considered to occur through several steps or elementary reactions. Each of the elementary reactions has a stoichiometry giving the number of molecules taking part in that step. Because the order of an elementary reaction gives the number of molecules coming together to react in that step, it is common to refer to this order as the molecularity of the elementary reaction. If, on the other hand, a reaction proceeds through several stages, the term molecularity is not used in reference to the obtained rate law. One step may involve two molecules, a second step only one molecule, and a subsequent step one or two molecules. Therefore, order and molecularity are ordinarily identical only for elementary reactions. The following reaction is an example where the molecularity and the order are not identical. This is the reaction which is the reduction of ferric by iodide. Two molecules of ferric reacts with two molecules of iodide to give two molecules of the ferrous and iodine in solution. Experimentally, it was found that doubling the concentration of ferric doubled the reaction rate, and doubling the iodide concentration increased the reaction rate by a factor of 4. Therefore, in this case, the order of the reaction with respect to ferric is a first order, the order of the reaction with respect to iodide is second order, and the overall order of the reaction is a third order reaction. Types of reactions. The reactions could be simple reactions or complex reactions. Simple reactions such as zero order reaction, first order reaction, and second order reaction. In zero order reaction, the reaction rate or speed is independent on the concentration of the reactants. In first order reaction, the speed of the reaction is dependent on the concentration of the reactant as a first order. In second order reaction, the speed is dependent on the concentration of the reactants as second order. Complex reactions such as a reversible reaction, where we have forward and reverse steps. In case of parallel or side reaction, the degradation occurs through more than one pathway. This is the series or side parallel reactions. In series or consecutive reaction, we have more than one step, and it is usually common in radioactive decay. Zero order reaction. In a zero order reaction, the reaction rate is independent of the concentration of the reactant. This is the rate of the reaction, which is constant, minus dC by dt equals K, and the sign is negative, which indicates a loss in the concentration. The rate equation is integrated between time equals 0 when the concentration is the original concentration, which is C naught, and time t equals t when the concentration equals Ct. The integration of the equations gives the zero order equation, which is the concentration at time t equals the original concentration minus the reaction rate constant multiplied by the time, and the unit of the reaction rate constant is mole per liter per hour. Okay. Half-life and shelf life of zero order reaction. Half-life is the time required for 1/2 of the material to disappear. It is the time required at which C has decreased to its half of its original value. The shelf life is the time required for 10% of the material to disappear. It is the time at which C has decreased to 90% of its original concentration. This is the half-life of a zero order reaction. We define C as half of the original concentration. Substitute in the zero order equation, the half-life equals 0.5 C naught divided by the reaction rate constant. In case of the shelf life, the concentration equals 0.9 C naught, which is the original concentration, and substitute in the zero order equation, the shelf life equals 0.1 C naught divided by the reaction rate constant. This is a graphic representation of zero order reaction, where a plot of the concentration versus time gives a straight line relationship, and the slope equals minus K, and the intercept equals the original concentration C naught. For first order reaction, the reaction rate is directly proportional to the first power of the concentration of one reactant. Means minus dC by dt is related to the concentration, and the negative sign shows that there is a decrease in the concentration. Rearrangement of the equation, dC by dC equal minus reaction rate constant multiplied by dt. Integration of the equation from the original concentration C naught at time equals 0 up to Ct at time equals t gives us the first order reaction equation. Natural log of the concentration at time equals t equals the natural log of the original concentration minus reaction rate constant multiplied by the time, or we can take it also as log to the base 10. Log C at time equals t equals log C naught original concentration minus reaction rate constant multiplied by the time and divided by 2.303, or we can also write it as an exponential relationship. Concentration at time equals t equals the C naught exponential minus kt, and the units of the reaction rate constant for a first order reaction is the inverse of the time. To calculate the half-life for a first order reaction, CT is defined as half of the original concentration. Substitute as CT is 0.5 C naught, half of the original concentration. The half-life of the first order reaction is 0.693 divided by the reaction rate constant. The shelf life is when the concentration equals 90% of the original value. In case of first order reaction, the shelf life equals 0.105 divided by the reaction rate constant. These figures show the graphic representation of first order reaction. When a plot of concentration versus time is made, a nonlinear relationship is obtained between the concentration and the time. The half-life is determined from the figure when the concentration is reduced to its half of the original value. This is the half-life. When a plot of log concentration versus time is prepared, a linear relationship is obtained in case of first order reaction, and the slope equals minus the reaction rate constant divided by 2.303. Apparent or pseudo first order. Apparent, it looks like. It describes a situation when one of the reactants is present in large excess or does not affect the overall reaction and can be held constant. The suspensions are considered usually as an apparent zero order reactions. Suspensions are example of zero order kinetics in which the concentration in solution depends on the drug solubility. As the drug decomposes in solution, more drug is released from the suspended particles so that the concentration remains constant. This concentration, of course, the drug's equilibrium solubility in a particular solvent at a particular temperature. The important point is that the amount of drug in solution remains constant despite its decomposition with time. The reservoir of solid drug in suspension is responsible for this constancy. The equation for an ordinary solution with no reservoir of drug to replace that depleted is first order expression, where A is the concentration of drug remaining undecomposed at time t, and K is the reaction rate constant for a first order system. When the concentration is rendered constant, as in the case of suspension, we can write it as a zero order reaction. As we mentioned, when the concentration A is kept or rendered constant in case of suspension, then the reaction rate constant, first order reaction rate constant multiplied by A equals K naught, which is a zero order or apparent zero order. K is the first order reaction rate constant, and A in this case is the solubility. The first order rate law becomes the change in the concentration by changing time, and E equals constant, which is the apparent zero order, while the apparent zero order equals the first order reaction rate constant multiplied by the solubility. Once all the suspended particles have been converted into drug in solution, the system changes to a first order reaction. Another example of apparent or pseudo order reaction, the hydrolysis decomposition reactions of drug molecules. Usually the hydrolysis of drug molecules is a second order reaction, but usually the amount of water present is in excess of what is needed for the reaction to proceed. Since it is the solvent, the concentration of water is considered as a constant throughout the reaction. In this case, a second order reaction behaves like a first order reaction and is called as an apparent or pseudo first order reaction. This is an example of a pseudo order reaction, a reaction of acetic anhydride with ethyl alcohol to form ethyl acetate and water. This is the acetic anhydride, and 1 molecule of acetic anhydride reacts with 2 molecules of the ethyl alcohol. The rate of the reaction equals the reaction rate constant multiplied by the concentration of acetic anhydride multiplied by the concentration of ethyl alcohol to the power 2. So what is the order of the reaction with respect to acetic anhydride, with respect to ethyl alcohol, and the overall order of the reaction? And if the alcohol is in large excess as a solvent, write the rate equation for the process and state the order. With respect to acetic anhydride, the order is first order. With respect to ethanol, it's a second order, and the order of the overall reaction is a third order. Once, if we have the solvent, if the alcohol is solvent and it is constant, is considered as a constant, then the alcohol will be a constant value in this case and will not change considerably with time. Therefore, it will be, the reaction would be pseudo first order reaction. This is also an example of an apparent zero order reaction in case of suspension. A prescription of liquid aspirin preparation is called for. It contains 325 milligrams per 5 ml or 6.5 grams per 100 ml, and the solubility is 0.33 grams per 100 ml. Therefore, the preparation will be definitely a suspension. The other ingredients in the prescription cause the product to have a pH of 6.0. The first order rate constant of aspirin degradation in solution is 4.5 10 to the power minus 6 seconds to the power minus 1, and calculate the zero order rate constant. Determine the shelf life, the T for the liquid prescription, assuming that the product is satisfactory until the time at which it has decomposed to 90% of its original concentration, which means 10% decomposition at 25 Celsius degrees. The solution for the previous problem, the zero order or apparent zero order reaction rate constant equals the first order reaction rate constant multiplied by the solubility, and it equals 1.5 multiplied by 10 to the power minus 6 grams per 100 ml per second B system. For the zero order reaction, in order to determine, or apparent zero order reaction, in order to determine the shelf life of a zero order reaction equals 0.1 multiplied by the concentration, original concentration, divided by the zero order reaction rate constant. 0.1 multiplied by the concentration of the whole suspension, not solubility, and divided by the zero order reaction rate constant equals 4.3 multiplied by 10 to the power 5 seconds, and it equals 5 days, which means that the shelf life of the suspension is 5 days.